Welcome to lesson 103. So in this lesson, we're going to go over how we can calculate the magnitude of vectors. We have briefly mentioned that magnitude basically represents, the size of a vector quantity. And as we are describing size, we should notice that magnitude is always positive. So let me write this down. And the idea behind it is really to use Pythagorean theorem to sum up, the size of a vector by looking at the x and y components. So here, if we are talking in two dimension, I have a position vector here, OP, that with endpoints A and B. So that implies that the x component has a length of A and the y component has a size of B, which forms a right triangle here. So geometrically speaking, the magnitude of the vector u then can be calculated using a squared plus b squared, all square root. Basically, that's the Pythagorean theorem. So now going to a three-dimensional space, we can see that the formula to calculate the magnitude of vector OA is given as x squared plus y squared plus z squared, all square root. Where did this come from, right? So first, you can imagine that we're talking about the first right angle triangle, which is O, X, and Y like that, kind of like in the base of the prism here. This is actually a right angle triangle, which tells me that this length here, the hypotenuse of the right triangle, is technically x squared plus y squared, all square roots, right? This part here. And then we're going to look at a second right triangle, which is between OA, the height of the box, and the hypotenuse that we just mentioned. So the vertical height here, it actually is another right triangle. So now if I square that original, hypotenuse, and then plus the square of the height, which is z, and then we're going to get, the length of OA squared. So in that sense, I have x squared plus y squared plus z squared, all square root, okay? And then if a vector is given in the form of a column vector, basically you have the first component, or x component is A, y component is B, z component is C. It gives you the same idea as a 3D vector, so the length or magnitude of the vector AB is a squared plus b squared plus c squared, all square root in this case, okay? So I'm going to get rid of these, just not to confuse you when you look at the notes, all right? So using what we just learned, let's calculate the magnitude of the following vectors. So first of all, we have vector A, -5 and 12. So I can say that the magnitude of vector A is -5 squared plus 12 squared, all square root. This is 25 plus 144 under square root 169 square root, which is 13 units. Okay. Question B, here we have vector B, -I plus 2j plus 3k. So to find the magnitude of B, I have to take the x component, -1 squared, plus the y component, 2 squared, plus the z component, 3 squared, all square root. So here I have 1 plus 4 plus 9, so 14 square root. Okay. In example 2, here we are asked to find the distance between the following pair of points. So the distance here can also be described as either the magnitude of the vector PQ or the magnitude of the vector QP. I don't really have to graph out these 2 points because I just know that by connecting the 2 points, I got a line segment. So here, just to keep things simple, I will just call this the magnitude of PQ is what we're looking for. And we know that to find the vector PQ, we can subtract the position vectors OQ minus OP. Okay, and so I have -6, 4, 0 as position OQ minus 2, 3, -1 as position vector OP. So -2, -3, minus -1, so +1. And don't forget, we're calculating the magnitude of this vector. So x component works out to -8. Y component is 1. Z component is also 1. So 64 plus 2, I have square root of 66 units, just like that. So now let's look at what's called unit vectors. The name unit vectors basically describe vectors that have a magnitude of 1. Okay, so some examples of unit vectors would be I, J, and K, your standard basis vectors, right? Because all of these have a magnitude of 1. So I say that if I have a non-zero vector, vector A, then I can find the matching unit vectors of vector A by finding a scalar multiple that will turn this vector A into a new vector pointing in the same direction that has a magnitude of 1. Okay, that's basically the idea. So as you can see here, the unit vector U can be calculated by multiplying 1 over the magnitude of A times A, because A will give us the direction, right? And this will give us a magnitude of 1. No, that's confusing. But you know what that scalar multiple does, okay? So let's take a look at example 3. Find a unit vector in the same direction as U of 0, -7, and 1. So simply following, sometimes we'll use a U hat to indicate we have a unit vector. We can say that 1 over magnitude of, let's call this A, I don't like to call this U. This is better, okay? So A here, and then A, that's what we're looking for. All right, so magnitude of A is 0 squared is 0, 7 squared 49, 1 squared is 1. All square root, and we multiply that by the vector itself. Okay, so I have 1 over square root of 50, which is square root of 25 times 2, so 5 root 2, and then 0, -7, and 1. So theoretically speaking, the unit vector will be 0, -7 over 5 root 2, and 1 over 5 root 2. Okay. Example 4. Find the vector of magnitude 7 that is parallel to the vector, let's call this A again, I don't like to confuse you, equals to 3i minus 4j. Okay, so the vector A, 3i minus 4j, obviously it does not have a length of or magnitude of 1, right? Because it's a 3, 4, 5 triangle. So that means in order to convert this into, a new vector that has a magnitude of 7, it would be convenient for us to actually find a scalar multiple of the unit vector of A that has a length of 7, right? Because the unit vector has a length of 1, multiply that by 7. So 7 times 1 over the magnitude of A times the vector A. So what do we have here? 7, 3 squares, 9, 16, and then 3 and minus 4. So obviously we're going to have 7 over 5 times 3 and negative 4 as a vector. If we like, we can write it back into component form. So 7 over 5 we said, right? So 21 over 5i, and then minus 7 times 4, 28 over 5j, that is. Okay? And then example 5. Here we have two vectors u and v given to us. We're going to find possible values of k such that the magnitude of the new vector ku plus v is square root of 62 units. All right. So here I want k101 plus the vector 3, negative 1, and 2, the magnitude of that to equal to 62. This becomes the vector k plus 3, minus 1, and k plus 2. Which means that I need k plus 3 squared plus 1, negative 1 squared, 1, plus k plus 2 squared, all square root to equal to 62. So by comparison, the radicands should equal to each other. So what do we have here? K squared, another k squared, 2k squared. Plus 6k plus 4k, so plus 10k when I expand both brackets, right? I have 9 plus 1, 10, plus 4, plus 14 equals to 62. So making more room on the side. Here I have to solve a quadratic, so 2k squared plus 10k, 14 minus 62, that's negative 48, equals to 0. To make it easier, I can factor out the 2. And let's factor this, 24, 5, so 8 and 3. So plus 8 and k minus 3. Okay, therefore, k must equal to negative 8 or k must equal to 3. And since k is just a scalar multiple, both of these answers are valid. Okay, so moving on, we are in number 6. So we have vector x and y are unit vectors, so both of them have a magnitude of 1. The angle between them is 60 degrees. Let's calculate the magnitude of 3x minus y. All right, so here 3x means that I have a vector that is 3 units long. So let's call this 3x. The angle between two vectors is measured from tail to tail. So that means if I go to the tail of this vector 3x, take 60 degrees here, and go 1 unit, I should draw the vector y. Okay. I want the resultant of 3x minus y. So y is going up to the right, negative y goes down to the left. Another way to do a vector subtraction is to think about a tail-to-tail configuration, because then I do 3x minus y and then I just close off my triangle like that. This is the vector 3x minus y. Okay? Because if you kind of like compare that to drawing heads to tails, so minus y, right, would be going this way. And then you will get the exact same vector. Okay, it's like a parallelogram. Okay, anyway, I need the magnitude of that. Looks like it's cosine law because I have a SAS triangle. Okay, so the magnitude of 3x minus y is opposite from the given angle. Is equal to the magnitude of 3x squared plus the magnitude of y squared minus 2 times 3x magnitude of y and cosine of 60 degrees. Okay, so this is 3 squared plus 1 squared minus 2 times 3 times 1. Cosine 60 is 1/2. All right. And so what have we got? 9, 10 minus, well, the 2.5 cancel, so minus 3. This is 7, so this is square root of 7 then for the magnitude itself. Square root. Okay. And now we have to determine a unit vector in the same direction as 3x minus y. Well, now we have the magnitude. It's easy to find the unit vector because all we have to do is take 1 over the magnitude of 3x minus y and then multiply by the vector. Okay, and then so I have 1 over root 7 and times 3x minus y vector. And then I have 3 over root 7, or this can be written as 3 root 7 over 7, x minus root 7 over 7, y, just like that.